Welcome everyone to today's webinar. Today, we are going to be going over reducing boiler emissions and achieving sustainability goals. I'm Michael Sipes. I'll be your host today. Two presenters are with me today. Peter Eoff, he's been working in the boiler burner industry for about 15 years. He's been working on helping boiler rooms have a sustainable future and how to prepare them for future regulations that might be coming along the line. David Eoff is also with me. He will be presenting the second part of the webinar today, talking about how Preferred Utilities works with their customers to achieve their sustainable goals. David Eoff has been working on boiler burner systems for about 30 years, and he's actually worked in California for the first few of those, helping California industrial facilities meet regulations. Thank you both for being here. It's an honor to have both of you, and we're going to go ahead and start the webinar now. But if you do have questions, feel free to put the questions in the right side questions tab, and we'll be getting to those afterwards. Otherwise, you can email Peter Eoff, which his email is also in the questions tab. You can also just wait till after the webinar and then email or put the questions in. Either way works for us, and we'll be definitely getting to your questions. Thank you for coming today, and Peter, take it away.
Good afternoon. On behalf of Preferred Utilities and Dave Eoff and myself, thank you for participating in today's webinar. Our contact information is on our website and on this slide. Today's topic is reducing boiler emissions and achieving sustainability goals. In this case, the egg came first, with the Clean Air Act being established in 1963 to study and clean up air pollution. In 1970, a stronger Clean Air Act was implemented, and the EPA was created to enforce the law. In 1990, authority was expanded to enforce the regulations and the establishment of the National Ambient Air Quality Standards. And they followed 6 common air pollutants: particulate matter, ground level ozone, carbon monoxide, sulfur oxide, nitrogen oxides, and metals such as mercury and lead. Primary standards set limits based on human health, while environmental and property damages are addressed in secondary standards. Areas that are cleaner than the primary standard are called attainment areas. Areas that exceed the primary standards are non-attainment areas. Ozone and ozone transport. Ground level ozone is formed from VOCs, volatile organic compounds, and nitrogen oxides. Primary sources are cars burning gasoline. Other sources include chemical plants, certain chemicals, and power plants. Geography and location play a large role in a city's GLOW, or ground level ozone, or smog. That's the reddish-brown tint you see over some cities. But it can be influenced by lay of the land, temperature inversions, and upwind contributors. For example, New York City metropolitan area has a large problem, and that's led to the formation of the Northeast Mid-Atlantic states, forming the OTR, or Ozone Transport Region, and they've accepted more aggressive limits to their emissions. So these are the Clean Air Act National Ambient Air Quality Standards table. You see carbon monoxide standards of 9 ppm, nitrogen dioxide, primary standard of 100 parts per billion, ozone, particulate pollution, and sulfur dioxide. The limits can be lower in certain regions, but cannot exceed these national standards. If you ever notice a spec or documentation, quite often is expressed in pounds per millions BTU. This is the way you convert from parts per million to pounds per million BTUs for the various fuels, as well as for the chemicals, the pollutants that we are going to be talking about today. So this is a handy chart to print out and save. Surveys show that the public perception is we are emitting more today and air is getting much worse. Despite this overwhelming perception, the U.S. is doing quite well. And Actually, the developing nations are contributing to most of the world's pollution. As you can see in this table, the EPA is tracking air quality from 1980 to 2018. Carbon monoxide emissions have gone down by 83% in those 38 years, lead by 99%, primarily through taking lead out of car fuel, gasoline. Nitrogen dioxide is down by 65%. Ozone is down by 31%. They didn't collect particulate matter data back then, not until 2000. And sulfur dioxide emissions are down by 91%. Here's another way to look at it, a nice, little easier to look at graph, where the center line of the x-axis is the most recent national standard. As you can see, all the various pollutants are tracking down and are considerably below, most of them are considerably below the national standard. The U.S. NOx air quality from 1980 to 2018, as you can see, we're above what is now the national standard of 100 early on, but about the early 2000s, we dropped below that standard, and today we're quite a bit below that. And that's measured daily max 1 hour averages. Since most of us are in the Northeast, this is a graph showing the Northeast emissions from 2000 to 2018, the same daily max 1 hour average. So that's a 34% decrease in the regional average. There are three main ways to reduce emissions. There's pre-combustion choices, there are combustion methods, and then there's post-combustion methods. We're going to discuss those separately. Fuel selection is one of the most important factors in minimizing emissions. As you can see, these are expected emissions of NOx and carbon monoxide from natural gas combustion combusted in various types of boilers, large wall-fired boilers, small boilers, tangentially fired boilers, as well as residential furnaces. The emission factor rating simply indicates the quality of the data, the number of sample sets that they have to back this data up. Another table here, these are emission factors for the criteria pollutants and greenhouse gases from natural gas combustion. And those are listed, carbon dioxide, lead, NOx, particulate matter, sulfur dioxide, total organic compounds, methane, and volatile organic compounds. Now, most of these statistics you're going to see are going to be corrected to 3% oxygen. So it's very important that you do that, and not very many installations are right at 3%. So when you look at the raw data, you always must correct it to 3% oxygen. David, is that wet or dry oxygen?
It really doesn't matter. If you're measuring NOx wet, you would use your wet O2. If you're measuring NOx dry, you would use your dry O2.
Okay.
As long as you're consistent, the formula works.
It is important to note that combustion has pass-through components. Pollution from sulfur, lead, mercury, and particulate matter are not influenced by combustion technology. They're in the fuel and pass through the combustion process. Table 1.3.1 shows various fuel oils emissions, expected emissions for SOx, NOx, and CO for different size types of fuel oils. And it's important to see the differences in residential furnace, as well as the previous slide, the natural gas emissions. So far, we've discussed pre-combustion techniques to reduce emissions, mainly fuel selection. Next, we'll talk about operational changes, but I want to take this time to point out the EPA website and the wealth of information that's available there. Earlier, you saw air trends that came right off of the EPA website, and recently just saw the statistics on fuel characteristics, and all this and more information is available at epa.gov. So next we're going to start talking about operational changes to reduce emissions. Obviously, there are things like good boiler tuning and lean excess air that can improve performance and efficiency in any operation. But mainly we'll be discussing the reduction of pollutants that are not pass-through pollutants, but optimizing combustion and efficiency by improving the combustion process. So focusing on NOx emissions, NOx is usually 97% nitric oxide and 3% nitrogen dioxide, but it is formed in three distinct different ways. It can come from fuel NOx, thermal NOx, and prompt NOx. Fuel NOx is oxidation of the nitrogen molecules attached to the hydrocarbon chains inside the fuel. The thermal NOx is NOx formed by disassociating nitrogen molecules in the air that join with the oxygen in the air to form nitric oxide. So two distinct different areas and sources for the nitrogen. And finally, prompt NOx, which is formed from the rapid reaction of atmospheric nitrogen with hydrocarbon radicals. Now, I wanted to insert here where we've seen pollutants characterized in a few different engineering units. When you see pollutants characterized as parts per million, it's important that you correct for the oxygen level in the stack because that influences the statistics. You take the formula shown here, actual NOx times 20.9 minus 3 divided by 20.9 minus your actual measured oxygen. And this works for CO as well as any of the other stack pollutants. Fuel NOx reduction, oxidation of the fuel-bound nitrogen molecules that are attached to the hydrocarbon chains. Single burner fuels, the only way to do it is by burning cleaner fuels. Multiple burner boilers, larger boilers, can use fuel staging techniques to reduce NOx. And the approach there, the strategy is to convert the hydrocarbon fuel to carbon monoxide in a sub-stoichiometric or fuel-rich environment, and then convert the CO to CO2 and water vapor in a high excess air environment. This can be done in utility boilers through burner tuning over fire airports and putting some burners out of service. Obviously, these methods are not available in a single burner boiler or furnace, and the only way to achieve that is by changing the fuel. Thermal NOx reduction. The disassociation of nitrogen molecules in combustion air follows an Arrhenius relationship, which means the percentage of nitrogen molecules broken into nitrogen ions has a logarithmic relationship to temperature. So to reduce the thermal NOx, combustion engineers reduce the peak temperature of the flame. This is done with burner fuel and air staging to slow combustion and flue gas recirculation that spreads the enthalpy of combustion over a higher mass flow denominator and lowers the oxygen content at the flame so that more nitrogen radicals reform with other nitrogen radicals to make a diatomic nitrogen again, reducing the concentration of oxygen in the combustion zone, increasing the concentration of nitrogen in the combustion zone, reducing the peak combustion temperature, and reducing the amount of time that the combustion gases remain at the elevated temperature will reduce thermal NOx formation. This is a schematic of internal flue gas recirculation, and it's a smart design of the burner nozzles and a swirler. FIR is a NOx reduction technique applicable to boilers that burn gaseous fuels only. It is similar to FGR, except that a portion of the flue gas is mixed with the fuel instead of the combustion air. Use of this technique has several advantages. It lowers the peak flame temperature, reduces the oxygen concentration in the combustion zone, improves the fuel-air mixing, and reduces the time under NOx formation conditions. When the same volume of flue gas is used, FIR can be more effective at reducing NOx than FGR. To minimize possible confusion, caution should be exercised when the acronym FIR is encountered because it is used to represent both fuel-induced recirculation and forced internal recirculation. This schematic shows external flue gas recirculation, which accomplishes the same type of a thing by reducing the temperature, combustion temperature. And it is just the external feeding of the flue gas from the stack or the last pass of the boiler back into the combustion air, and where it mixes in the fan or the wind box and is reintroduced into the furnace. It is very effective against thermal NOx formation, but this technology is a little bit older and it goes back to the 1980s. Prompt NOx. The most effective NOx emission control strategy is one which NOx formation is reduced as much as possible and boiler performance is affected as little as possible, except in advanced burner concepts where air and fuel are premixed. Combustion at either low or very high excess air levels results in low NOx formation. For most low NOx boilers, the best combination of low NOx formation and high boiler efficiency occurs when the amount of oxygen is just enough to ensure complete combustion. Operation at very low excess air levels can cause problems. It can result in incomplete combustion and the formation of CO that causes boiler efficiency to decrease. In addition, it can create unsafe conditions inside the boiler that can lead to an explosion. CO emissions reduction. CO is caused by incomplete combustion. CO emissions in a typical boiler or furnace, realistically always less than 10 parts per million. CO emissions are caused by fuel-rich combustion, not enough air to mix with the fuel, and too lean a combustion where there's too much combustion air. And it can also be caused by flame impingement on the tubes or the furnace wall or cool refractory. The flame could be too small, so it's not getting above the critical 1400 degrees Fahrenheit. It is much more common to have CO emissions at low fire than at high fire. So, in summary, we've got NOx abatement methods. Fuel NOx, use a cleaner fuel. Thermal NOx, reduce your peak flame temperature. And prompt NOx, improve mixing and eliminate rich zones. And post-combustion treatment, which we're not going to discuss today, but just so you know, and it's also available on the EPA website, SCR and catalyst beds and chemical injections, and that area is really developing quite rapidly in the last few years. So with that, I'm going to pass the baton over to Dave Eoff, who will talk about carbon reduction strategies in the boiler room. Dave, the floor is yours.
Okay, so I'm Dave Eoff. I'm the sales manager at Preferred Utilities. I have been a burner combustion engineer since the early 1990s, and I actually worked in Southern California where low NOx technology really started with Rule 1146 that mandated that if your boiler didn't have a low NOx burner on it, you had to trash it and install a low NOx burner. So we were very busy retrofitting boilers to low NOx burners in the early 90s. And as those slides from Peter show, we've done a very effective job at reducing NOx emissions in the United States. So much so that when fossils like Peter and I talk about emissions, we assume we're talking about NOx and CO and SO2. It seems like anybody under 30, they don't know what air pollution really is in the United States. So when you talk to them about emissions, they immediately start thinking about CO2. And CO2 is what we're going to talk about now, and how you can reduce CO2 emissions in the boiler. So we're going to start small and end big, beginning with fuel efficiency improvements you can make in the boiler room. So it stands to reason that if you burn less fuel, you're going to release less carbon. And we've been using various technologies over the last 30 or 40 years as fuel prices have increased to increase the efficiency of burners for the economic payback. But by decreasing the amount of fuel you burn, you also decrease the amount of CO2. So what you can do, you can retrofit to a high performance burner that will lower excess air, increase burner turn down, and if you employ a control system known as oxygen trim, you can lower your real world excess air or your operating excess air even further. So efficiency gains of 5 to 8% of fuel consumption are possible, and that corresponds to 5 to 8% carbon emission reduction. Another thing you can do is you can reduce the amount of electricity you're consuming in your boiler room. We do this by replacing across-the-line motor starters with variable speed drives. And usually we will start with the biggest blowers or the biggest motors in the boiler room, and that's usually the forced draft fans on the burners. We might put VFDs on the induced draft fans, and sometimes we'll put VFDs on the feed water pumps. But typically we start at the largest motor because that's where the ROI is the most, and that's the FD fan. And the conversion between electricity and CO2 depends on where you are. And the way to calculate this is to go to the EPA's website. They have a calculator there called AVERT, which is an acronym for something or other. The national average is you release 7.07 times 10 to the negative fourth tons of CO2 per kilowatt hour reduced. That number varies from place to place depending upon how much fossil fuel is used to create electricity where you live. So the way the VFD works is by reducing the fan speed at lower boiler horsepowers, you reduce your electrical consumption. And this chart shows combustion airflow versus boiler horsepower. The top line is a traditional burner with an across-the-line motor starter that is somewhat analogous to driving with your foot on the gas and your foot on the brake at the same time. We run the fan at 60 Hertz and we throttle it back with a damper. When we put a variable speed drive on the FD fan, we'll use a little bit of damper control at low fire, but the goal is to get that damper open as quickly as possible as you move up to the higher firing rates. And then once the damper is full open, then we start increasing the VFD speed. So that gap between the top curve and the bottom curve is your brake horsepower or electricity kilowatt hour savings. So this is the equation you use to calculate electrical savings for different VFD speeds. It's 1 minus your actual speed divided by 60, all that to the third power. So if you run the FD fan VFD at 30 Hertz, your electrical savings is 87.5. At 20 Hertz, the electrical savings goes to 96.3. So there's a lot of electrical savings to be had by slowing down your fans. And the conversion, just as a reminder, is 7.07 times 10 to the negative fourth tons of CO2 per kilowatt hour reduced. To estimate the fuel and electricity efficiency gains possible with a burner and controls retrofit, you can use Preferred's online energy saver payback tool. You input the excess air, stack temperature, and load profile of your existing burner, as well as the performance of the proposed new burner, and the web app estimates your fuel, electricity, and carbon savings. You can input your fuel, electricity, and retrofit costs, and the web app will out an ROI for the upgrade. The web app doesn't calculate CO2 savings from the electricity reduction yet, but it's on our list of things for our programmers to do. But for now, you can use the AVERT calculation for your region. So the second strategy you can use to reduce your CO2 emissions is to switch from one fossil fuel to another, switching from a very carbon-intensive fossil fuel to a less carbon-intensive fossil fuel. And this chart shows the pounds of CO2 you produce per million BTU of different fuels. Natural gas is the lowest, and different types of coal are the highest. So I made this chart to show you what the percent reduction in carbon is switching from one fuel to another. So you start in the first column there. If you're switching from number 2 oil and going to natural gas, your carbon emissions reduction will be about 28%. And this is just based upon the stoichiometry of burning the different fuels. And if you remember your high school chemistry well enough, you can write out the stoichiometry equations and check me. All central steam plant boilers can be converted to natural gas firing, including field-directed water tube boilers, packaged water tube boilers, and packaged fire tube boilers. In most cases, new burners and controls will be required. So, burner retrofits require expertise in combustion and boiler controls for best results. In most cases, the burner will have to be replaced. Sometimes a new burner insert can be made to fit into the existing wind box. This video shows a crew replacing the burner in a trademarked Cleaver Brooks boiler with a new preferred burner. As you can see, with guys working really fast, this was done in 41 seconds. This was a fuel switching project at Bates College where they switched to a renewable fuel and achieved 82% carbon emissions reduction, but I'm skipping ahead. When you're doing a burner retrofit, it's important to include a vendor knowledgeable in both burners and controls that will walk the boiler room with a representative from the plant and make a replace or reuse decision for each of the following components: the windbox burner fan assembly, the flame safeguard fuel air ratio controls, instrumentation including pressure and flow transmitters, motor starters, and VFDs. Why spend money replacing perfectly good equipment if it will work with the new burner? So the final carbon reduction strategy we're going to talk about is converting from a fossil fuel to a renewable fuel. And the idea with renewable fuels is we are taking carbon that was already in the biosphere and burning it. We're not taking carbon that was 8,000 feet under the ground in the form of fossil fuels and putting that into the atmosphere. So when we talk about landfill gas or digester gas or some of the liquid fuels are going to come up in a few slides, this is carbon that was recently trapped and we're putting it back into the atmosphere. We're not taking long cycle carbon from the dinosaur period and putting it into the air. So everybody in the boiler burner industry is familiar with landfill gas and digester gas. Both are renewable fuels made from renewable sources. We've been burning these fuels since at least the 1980s. The problem is they're gaseous fuels that can't be economically transported any distance. And even if you had the real estate to put in a lagoon or a digester gas in the middle of your campus, you're not going to want to do it because of the smell. Preferred works with 2 suppliers of liquid fuels. Ensign manufactures a fuel called Renewable Fuel Oil, or RFO, and REG manufactures a fuel called Biodiesel Residual Oil. Both of these fuels are liquids, so they can be put on a truck or they can be put on a rail car and delivered directly to your facility from where they're made. This unphotoshopped picture is proof. So Ensign makes renewable fuel oil, or RFO for short. It's made from tree trimmings from harvest residues or commercial tree plantation thinnings. If this biomass wasn't made into RFO, it would be burned or left to decompose and the CO2 would have hit the atmosphere soon anyway. RFO has been approved for all regulatory credits for renewable fuel oils, including RINs and RECs. This is a very simple diagram explaining where RFO comes from. The end products are liquid smoke, renewable feedstock sold to petroleum refineries, and RFO for steam and hot water plants. By the way, when you burn RFO in your boiler, it produces a very nice wood smoke aroma. RFO is considered to be biogenic. So greenhouse gas emissions from RFO are about 88% lower than number 2 oil and 82% lower than natural gas. Virtually any fire tube or water tube boiler can be converted to fire RFO. RFO is acidic, so everything in contact must be made out of stainless steel. The greenhouse gas emissions reductions for this fuel, it's not 100% because it does take some fossil fuel to make the renewable fuel and to transport it to the plant where it's going to be burned. Ensign, the manufacturer of RFO, typically amortizes the cost of the fuel conversion in a 5-year fuel contract. Even with the fuel switching costs, the price of RFO is close to the price of natural gas on a comparable BTU basis. Preferred has converted boilers at 3 facilities to RFO: Bates College, Youngstown Thermal, and a CRNC facility in Ontario, Canada. So the video I showed you earlier was Bates College. They've converted 2 of their central steam plant boilers to RFO. As soon as our technicians finish tuning up the new burners, Bates issues a press release touting their success reducing greenhouse gas emissions at their campus. The URLs are there, or you can Google the words Bates and Renewable and you'll find these articles. Actually, last summer, Bates announced that they are greenhouse gas or carbon neutral, mainly because of efficiency improvements to the campus and converting their central steam plant over to RFO. Preferred is also working with REG, the nation's largest supplier of biodiesel. They make a fuel called Biodiesel Residual Oil. Think of bioresidual oil as the number 6 oil of biodiesel. It has the appearance of dirty French fry oil, but it has actually undergone extensive cleaning to remove impurities such as ash, heavy metals, and water. Preferred started burning bioresidual oil in our 2 shop boilers in June 2 years ago. The burner on the left is a 1950s vintage Preferred rotary cup burner designed to fire number 6 oil. The burner on the right is our state-of-the-art low-emissions Ranger burner. They are both burning bioresidual oil. This is the startup data from one of the 2 boilers. Important things to note include bioresidual oil needs to be heated to 160 to 165 degrees F. If the existing burners that you're trying to burn bioresidual oil in are using number 6 or number 4 oil already, they will have a pump and heater set that could be reused. Note, the combustion efficiency is similar to number 2 oil. Stack CO is less than 10 parts per million. This is considered clean combustion for any fuel. Opacity was 0 throughout the boiler load. In fact, these burners were firing number 6 oil before we changed them out to bioresidual oil. It took no new equipment, not even a new oil tip, to burn the bioresidual oil. Preferred's 2 boilers have been firing bioresidual oil all through the 2018-2019 heating season and the most recent 2019-2020 heating season with no unplanned downtime. We shut down these boilers each summer, we open them up, and we've found no unusual ash or sooting of the boilers. We fired them up again last summer for a show and tell with no issues at all. The price of bioresidual oil is generally less than number 2 fuel oil. Fuel switching costs vary widely depending on the existing combustion equipment. So the ideal bioresidual oil candidate is a facility that already has a pump and heater set, so already firing number 6 or number 4 oil. They can reduce their greenhouse emissions by up to 80% and spend less for fuel than number 2 oil. There are a lot of facilities in the Northeast that are still burning number 6 and are planning to switch to number 2 in the near future. These plants can switch to RFO or bioresidual oil and exceed all existing and proposed carbon emission reduction goals. So that's my part for reducing carbon emission in your boiler room. We're going to go live now and take your questions. You can email your questions to Peter Knopf, or you can put your question in the chat and we will take them there. And thank you for attending.
All right, thank you everyone for attending. We're going to go ahead and take your questions. If you guys have any, feel free to put them in the chat. We're going to take your questions based on the presentation that was presented. Dan, Wallace, and David Eoff, are you guys there?
I'm here. We're here. So Dan is sort of our special guest on this webinar today. He is the VP at Preferred in charge of research and development, and Dan has done most of the startups where we've converted boilers over to renewable fuels. And Dan, you just were put on a couple of very prestigious sounding boards. Can you tell me something about that?
Sure. The two UL boards, UL 795, UL 296. 795 is Underwriters Laboratory for gas burners, and 296 is Underwriters Laboratory for oil burners. It's good to be on those boards because it helps determine the safety standards for fuel burning equipment. kind of get an early view of the next update to the standards and be able to propose new rules that could go in there to help make future standards better.
Every once in a while, I'll have a customer that wants to violate UL or NFPA boiler code, and it's been wonderful having somebody on the steering committees for those boards to talk to them and let them know that, you know, what they're trying to do is a bad idea and doesn't comply with code.
Mm-hmm.
You're on an B.S.M.E board too, right?
Correct. The American Society of Mechanical Engineers, CSD-1. So for boilers that have a heat input less than 12.5 million B2s per hour, NFPA 85 does not apply. It falls under the guidelines of CSD-1. So being on that board is also critical to understanding that, you know, the latest set of standards that are going to govern units that size.
Okay. Michael, do we have any questions in the chat?
We don't have any questions in the chat, but we do have some questions that might be good to go over. One of the questions is, we talked about RFO in the presentation as it's being acidic. What about BRO?
So BRO stands for Biodiesel Residual Oil. Again, it is not acidic. You can reuse most of your existing equipment, as David Eoff said. When we converted our boilers here, we didn't have to change any of the fuel oil handling system because we already had number 6 oil in place or the burner. The only thing we had to do was the fuel oil heater that we have in place. We had to change to we had to change the internal element to be stainless steel, but the casing remained carbon steel, and all the piping remained the same. The other consideration is elastomers. Luckily, we had all the correct elastomers in place, but one thing to be on the lookout for biodiesel-based fuels is typically rubbers like nitrile rubber, Buna N, are not acceptable. They're not compatible with biodiesel or fuels like them. So we recommend going to either Viton or PTFE where possible.
So biodiesel residual oil is a hydrocarbon, so it really can't be acidic. But RFO is water-based, so it can be acidic, and it is. Has a pH of about 2. Dan, I'm working from memory.
That's correct. Yeah, it's similar for comparison to practical purposes. It's similar to lemon juice.
So it seems odd to have a water-based fuel, you know, something that's water-based be combustible. I guess the only other example I can think of that would be like the black liquor they burn at pulp and paper plants, right?
Right.
How does RFO differ from like black liquor or red liquor at a paper plant?
So RFO is produced from a feedstock of wood. So Ensign, they use wood waste that's sustainably harvested in the forest and then processed through fast pyrolysis. And through that process, they make a liquid fuel that is nominally 25% water, with the remainder being a hydrocarbon. And because it's coming from a sustainable source through sustainable forest practices, it qualifies as being carbon neutral.
Okay, and then economically, these fuels, both fuels we're talking about, RFO and BRO, were less than number 2 diesel last year when diesel was cheap, and now you know, a barrel of crude is going for $60-something a gallon. I would think these fuels would be even more economical now than they were last year.
That's correct. Yes.
Okay.
We did have a question in the chat. It's someone asked, what are the storage issues for both of the fuels? I know we talked about RFO being acidic, and then BRO, we need to change some of the fittings and stuff like that. But Dan, can you speak to that?
Yeah, sure. Good question. So with RFO being acidic, that particular fuel would require a stainless steel storage tank. So if there were an existing fuel oil storage tank that was carbon steel, it would need to be replaced with a stainless steel version. With bioresidual oil, it is not acidic, so the existing storage tank could be left in place. It doesn't need any special changes to it. One thing to consider is it's very similar to handling number 6 oil. You want to keep the oil hot because it does start to thicken as it gets colder, become more viscous. So it's important to keep it typically above 120 degrees Fahrenheit, and to keep it from turning into we call it butter here. I mean, that's basically what it looks like, you know, when a dark butter, when it becomes more viscous and it melts just like it. So once it gets above 120, 140 degrees again, then it flows very freely.
So we developed a butter layer in our tank soon after we started burning bro. And what was the solution to the butter layer in our tank?
Yeah, that's a good question. So with the remnants of the system we had in place from number 6 oil, we had the means to recirculate oil through a heater back to the main oil storage tank. So we kept that same system in place, and we set the thermostat to be at 140 degrees Fahrenheit. And so the heater would stay on while recirculating fuel back to the tank until the fuel reached that threshold, and we store it that way.
And then we use a trim heater to get it up to 160, 165 at the burner?
That's correct. And it depends on the particular burner, but in general, 160 to 165. Our legacy burner, the rotary cup burner, which is on one of our boilers, has been there for, I would say, 30 years now. And it was meant to be a residual fuel oil burner, and it can burn bioresidual oil even down to 140 degrees Fahrenheit.
Also, the other thing I did want to mention, we talked about when talking about with Rfo, and Dan, you kind of spoke to this, which is we talk about how Rfo is harvested from trees, and
Yes.
I know that Ensign does a pretty good job and a really miraculous job of kind of they don't look for clear cutting. They work with, I think, one of the national organizations, and they find forests that need to be trimmed. And instead of just burning those trimmings, they try to turn those into Rfo. Is that correct? They don't just clear cut the forest.
That's exactly correct. So sustainable forest trimming is very important to preventing forest fires. As you know, when a forest fire occurs, it's a tremendous hazard for the environment because of all the CO2 emissions generated, not to mention, you know, all the other harmful particulate and so on and so forth. So by having sustainable forest practices where trimming can be done to prevent that type of scenario, you get the double benefit of reducing the carbon emissions from a forest fire, and then also that wood that would be in there would decompose and turn into CO2 anyway. So it's no net gain in CO2 to the atmosphere over time.
Great. We did have a question. Someone asked regarding FGR usage to reduce emissions. Is there a time when you can just use too much FGR?
Right. So it depends on the burner technology, and each burner is a little bit different, but there can be a point where too much FGR can blow the flame out and cause instability issues. Typically, most burners can withstand about 20% FGR. If it's an ultra low NOx burner, some burners are designed to take up to 40% FGR, but typically not more than that.
And when Dan mentions FGR, he's talking about mass percent, and there's two ways to measure how much FGR is going through your burner. One is to measure the oxygen in the wind box, and fresh air has 20.9% oxygen. For every 1% O2 drop in wind box O2, that's about 5% FGR by mass.
Right.
The other way is to use the temperature of the flue gas, the temperature of the ambient air, and the temperature of the wind box air, and do a little bit of math and determine what proportion of the wind box air is hot flue gas recirculation. But I think O2 is most reliable, and anybody tuning a boiler is going to have an analyzer that measures O2, so they'll just take their analyzer probe out of the stack and stick it in a port in the wind box, and they'll know how much FTR they're recirculating.
Right.
Okay, looks like that's most of the questions. Do you want to just mention about usage of Rfo and Bro regarding different types of applications, talking about heating for a facility and then process use, Dan?
Yeah, sure. So typically Rfo and Bro, they to get the renewable energy credits, they typically have to be used for the code calls it comfort heating, whereas a process load, typically you don't get the benefit of the RINs. I mean, certainly they can still be burned and they may even be economical, but the renewable energy credits are typically only for comfort heating.
Got it.
Dan, has there been any new news on the regulatory front for Rfo or Bro?
Not recently. There is talk about reinstating some of the renewable fuel standards that would be applicable to both Rfo and to bioresidual oil. For each fuel has its own class of RINs that it's in, and it depends on how abundant they are. So for instance, with biodiesel being relatively abundant and bioresidual oil falling under that category, the value of a RIN for bioresidual oil is a little bit less than the value of a RIN for renewable fuel oil, because renewable fuel oil is a cellulosic fuel, whereas biodiesel is a methyl ester is the name for it.
Okay, thanks. So the most common question I get emailed to me after these webinars is, can I get a copy of the presentation? And the answer is yes. Email me or email Michael. My email address is on the screen now, and we'll send you a copy of this presentation. So Dan, I want to thank you for your time this afternoon. This was excellent. And Michael, thanks for putting this together with no technical glitches again.
Hey,
So,
we're on a roll.
All right, thanks guys.
Thank you.
Thank you for everyone.